Thank you, everyone. My name is Qun Zhou. I prefer you call me QZ instead. So today I'll be talking about NanoGrid Testbed. This is a collaborative project with Orlando Utility Commission. A little background about myself. So I do research in smart energy systems, smart grid, smart buildings, and I direct the SIDO, Smart Infrastructure Data Analytics Lab, and I teach courses in power system economics, in data analytics, in energy systems. I collaborate with OUC, Siemens, and Rail. So about the project, NanoGrid is actually a testing site in OUC Gardenia site. It has multiple components installed, distributed energy resources. Start with PV panels, have a total about 60 kilowatts PV solar panels, including floating solar arrays and rooftop PV panels. And then we have two vanadium flow batteries. The charging rate is total of the two is 20 kilowatt, and then the total capacity is 80 kilowatt hour. And two flywheels battery just recently installed. The total charging rate is 16 kilowatt, and the capacity is 64 kilowatt hour. And we have vehicle to grid, V2G charging station. The charging rate is about 15 kilowatt, and we have one DC fast charging station. The charging rate is 50 kilowatt, but it also has a function of level 2 AC charging, and then two dual port AC charging stations. So we can see that the components here are covering basically power sources and energy storage components in power consumption, which are the in the side they have a fleet building and an office building that consumes power, and also you have electrical vehicles that charge power as well. And then our job is to help them to develop a nanogrid management system. In this picture, you can see that's the system we developed for them. It's mounted here, and it's general computing device, and we develop this management system to control different components of the nanogrid, and then based on some predefined operational functions. One of the functions is called solar. Well, these are just a couple of functional modes. So we have solar smoothing modes, which tries to flatten or slow power ramps due to weather effects on PV outputs. So it can, when clouds passing by, the solar power drops, and when it goes away, then the solar power increases. These are pretty sudden changes that the power grid does not like. So we try to dispatch batteries or EVs to help smooth out the solar power. And the second function mode is called EV demand mitigation. This is try to help the scenario where you have very high EV penetration, that everybody starts charging EVs when they arrive in the working place, and it could basically increase the total power grid demand, which is undesirable for the grid either. So we try to minimize the impact of EV charging on the existing demand of the OUC site. And we also look into contingency events. Basically, we try to handle the control during an event where the grid power is not available, but the NanoGrid site or the campus still needs the power. Here, this is a use case example, the solar power smoothing one. On this picture, you can see this is floating array in a lake, on a lake or pond. So the clouds can be really, rapidly changing. So the blue curve on the right-hand side shows the original power output. It's very volatile. You have big jumps and dips. And then if we dispatch the battery and EV, we can help smooth out the solar power. The yellow curve shows that, the smooth curve, which is much better for the grid operators to actually, and also for the grid, devices, those tap changers or transformers, they would perform much better with smoother curve. This more. The battery signals look like this. This is the control command that we send to the battery. The battery they are vanadium flow batteries, so they are very responsive and flexible, and they have a very long lifespan. So after that, you can see the ramp rate is. We can still see there's some, some points that actually out of the band, the ramp rate limits, but it's much better. And these jumps and dips, they can be further alleviated use voltage control devices in the grid. And these, I'm gonna show you a few pictures that about the dashboard. So the control has a dashboard. The control management system has a dashboard that we developed. Basically, you can see all the data, solar power output, irradiance, and the daily profile of it. And you can also see the battery state of charge. And these weather profiles, real-time data, including temperature, precipitation, wind speeds, precipitation, humidity. And then you also have a historical data that can select the daily file, monthly file to see the patterns of that particular time period. And then these are the basically the parameter inputs that operators can adjust. They can adjust the different functional mode and also change the the ramp rates and different charging stations, battery selections. They can also adjust the battery charging rate manually, bypass our algorithm. So some of the challenges in the lesson we have learned. One of the biggest challenges is establishing the communication between all the devices, because they're mostly on Modbus protocol, but still there are registers we have to learn, and then there are missing data. Sometimes we send out the data request, we have to wait, and handling data collection. Also, we need to make sure the data and the control commands send in the correct sequences to avoid some kind of threshold or safety threshold to make sure everything works properly. And then the timing of the algorithm is also challenging because it's a real-time control, and we constantly send the data request. Basically, well, right now it's every 5 seconds, but then we need to set up response time, usually within milliseconds level. And then we have to also check if the devices have received the control commands and respond properly. There are more to be done in the project that we need to develop algorithm for pre-storm planning to prepare the nanogrid for extended outage. Then if there is a outage event, then we have to transition the nanogrid into islanded operations. After the grid is restored, then we have to reconnect the nanogrid to the grid. And then we're planning to integrate a more advanced solar forecasting model, including the cloud image system, to improve the solar smoothing operation. And then we need to do real-time demand metering for demand mitigation, including the 2 buildings on site. And we also need to do, we integrate the vehicle to grid charger. Right now, they are in one of them functional mode, but not all of them. So we have to consider that. And yeah, that's it. And I would like to acknowledge the OUC Emerging Technology team and my research team. And that's it. And some pictures to enjoy. Thanks.